we know that there are two types of fields in electricity. One of them is electric field, the other one is magnetic field. In section 2, we'll talk about magnetic field in details. Now I'm going to slightly talk about the electric field as well. This electric field is very important for understanding some titles in the 12th grade. We know that every charged particle produces electric field. We talked about this before. So there are two types of charges, positive and negative. So positive charge, protons represent positive charges, electrons represent negative charges. And electric field around the proton is radial outward. So lines of the electric field goes like this, radially outward. And for a negative charge, electric field around the negative charge is radially inward. Their directions are opposite. Are these electric fields uniform or not? Uniform or not? Remember, in solenoid we talked about that inside the solenoid the magnetic field is uniform. Why? Because lines are parallel. If magnetic field lines are parallel, we can say that it is uniform. Tell me now, these lines are parallel or not? Not parallel. It's not parallel. This electric field is not uniform around these charged particles because lines are not parallel. So then, how can we produce a uniform electric field, if the question is this? We are going to use two plates. Plate means two parallel to surface, like this. This is called a plate. If we use two parallel plates, conductors, like two copper plates, or two aluminum plate, or any other metal, okay? If we use two parallel plates, but this plate must be charged, oppositely charged plates. One of them is positive, the other one must be charged negative. And we studied in section 1. Electric field lines start from positive, ends at negative. So from positively charged plate to negatively charged plate, we are going to see that electric field lines are formed. Now look at those lines. Are they parallel? So if they are parallel, can we say that it's uniform? Yes. This is the method of producing a uniform electric field. Lines, electric field lines must be parallel. How could it be parallel? If we use two plates, one plate is going to be positively charged, other plate is going to be negatively charged. Then electric field lines will form from positive plate to negative plate. But how can we charge a plate positively and negatively? How can we do that? We are going to use batteries. You know batteries have positive terminal and negative terminal? Yes. So this is the symbol of a battery in electric circuit. One terminal is positive for battery, other terminal is negative. If you attach positive terminal of the battery to one plate, that plate becomes positively charged. If you attach negative terminal of the battery to other plate, it becomes negatively charged. Then electric field lines will form from positive plate to negative plate. This electric field is a uniform electric field. And this electric field can be calculated by the equation delta V over D. What is delta V? Potential difference of the battery. So on the surface of each battery, you are going to read a potential difference, as, for example, remote control devices. Take one or two battery, look at the surface. Written 1.5. And each battery has a potential difference, 1.5. If this battery has a potential difference of 1.5 volts, of course potential difference between the plate must be 1.5. Whatever this potential difference is between the plates, it's going to be again 1.5 volts. Then if we divide this potential difference by the distance between two plates, which is D, we can calculate the magnitude of this uniform electric field. So we are not going to calculate it, but the units are important for us now, for the 12th grade. What is the unit of delta V? Volt. What is unit of distance? Meter. So that if I ask you, what is unit of electric field? Volt divided by meter. This is one of them you have to know. What is unit of electric field? Volt divided by meter. And now I am going to set an electron inside this electric field. I'm going to set an electron inside the electric field, just like this. This electric field will set a charge into motion, just like gravitational field sets objects into motion. Okay, this is the pen. It's in my hand. If I release it, what will happen? It will fall down. Why? Because of the gravitational force. Gravitational force will take this pen down to the ground. And let's write the equation for gravitational force. It is Fg. Gravitational force is equal to mass of the object multiplied by g, which is the free fall acceleration. And we know that acceleration is a vector quantity. G is a vector. What is the direction of the g? Downward to the ground. So any scalar quantity, which is mass, a force is also vector quantity. A mass is always positive, correct? Then, if this mass is always positive, mathematics tells you that this g and Fg are always in the same direction. Yeah, g is downward, Fg is also downward. Can I apply this rule to electric field? Yes, we can. Instead of mass, what will come? Charge. Because this is a charge, represented by Q. Instead of gravitational field, we are going to write electric field. Instead of gravitational force, we are going to write electric force. Yes. If you put a charge inside an electric field, there will be a force acting on this charge. If this charge is positive, can you say that Fe and E are in the same direction just like Fg and G? Yes. If charge is positive, yeah, if you put a positive charge inside this electric field, a force will act on this charge in the same direction of electric field. Yani Fe and E are going to be in the same direction. So what is the direction of the electric field in here? From left to right. So that's why electric force will act on this charge from left to right. What if I put an electron? Put an electron inside the electric field. So if this is negative, so one vector is negative of other one. Those vectors have opposite interactions. For electrons, for negative charges, electric force will be in the opposite direction of the electric field. Electric field is from left to right. For negative charge, electric force is from right to left. Opposite. This is the rule. This is the rule. I will take your question just a minute. For positive charges, electric force acting on the positive charge and electric field are always in the same direction. But if the charge is negative, electric field and electric force are always in opposite directions. This picture is from chapter 9. We are going to talk about this in chapter 9 as well. Look at here. Electric field is from left to right. Okay, look at now direction of the motion of positive charge. Positive charge moves in the same direction of the electric field. Why? Because force is in the same direction of the electric field. That's why if you put a positive charge inside an electric field, it will move in the same direction of electric field. If you put a positive charge inside an electric field, it will move in the same direction of electric field. But for negative charge, you get them? So negative charge always moves in the opposite direction of the electric field. So this will help you right now in chapter 6, chapter 5 also will help in chapter 9. So electric field, when you put a charge inside an electric field, this electric field will set the charge into motion. What does it mean? It causes charged particles to start moving. Yani only electric field does this. No other field can do that. If you want an electron to start motion, you have to use an electric field. And this electric field will set electron into motion in the opposite direction of the electric field. If you put a positive charge inside an electric field, this positive charge will start moving, but in the same direction of electric field. So we can start motion of a charge only by electric field. So electric field sets a stationary. What does stationary mean? At rest. Electric field sets a charge which is at rest into motion by applying an electric force on the charge. But this electric force in the same direction with electric field for positive charge, in the opposite direction with electric field for negative charge. Now negative charge always start moving in the opposite direction of electric field, But positive charge always moves in the same direction of electric field. So if I rewrite this equation, F is equal to Q times E, can I write it E is equal to F over Q?
Yes.
Yes. So what is the unit of force? Newton. What is the unit of electric charge? Coulomb. Then what is the unit of electric field? Newton per Coulomb. So we got two units. One unit is volt per meter for electric field. Second unit is Newton per Coulomb, which means they are equal. Yani 1 volt per meter is equal to 1 Newton per Coulomb. Sometimes in unit conversion, chapter 5, we need that. Guys, instead of volt per meter, you will get sometimes Newton per Coulomb. If Newton per Coulomb is given, so you can say that it's equal to volt per meter. They are equal. Now, in this part, you should know two things, really important things. One of them is only electric field sets stationary charges into motion by applying a force. Only electric field sets, and starts motion of a charge by applying an electric force. And the electric force is in the same direction for positive charges, in the same direction with electric field. For negative charges, in the opposite direction of electric field. So this is crucial for this chapter, also for chapter 9. Also better to know this, because there are two equations for electric field, there are two units for electric field. Volt per meter and also Newton per Coulomb. They are equal units. Okay, now let's continue. So now, this is representing two parallel plates, charged parallel plates. Lower plate is positively charged, upper plate is negatively charged. And we know that electric field forms from positive plate to negative. So what is the direction of the electric field? Up to the pole. If you put an electron inside, of course, there will be a force acting on an electron, which is in the opposite direction of electric field. So downwards. This charge will start moving. If I can explain that. If you put a charge inside an electric field, this charge will start moving. That's why we said that. Electric field sets a stationary charge into motion. Yani, if you want to move a charge, if you want to start the motion of a charge, you have to apply an electric field. Electric field will do that. So electric field sets a stationary charge into motion by applying an electric force. Look at the direction of the electric force. Downward?
Yes.
Electric field upward? Are they parallel?
Yes.
Yes. Electric force always parallel to electric field. Sometimes in the same direction for positive charge, for negative charge, in the opposite direction but parallel. What if we put this electron not inside an electric field, inside a magnetic field? You know what? The natures are different, huh? Electric field is for any charge around, but magnetic field is on charges by motion. The natures are different. If you put a charge, say that electron, inside the magnetic field of this magnet, right here, at rest. So, magnetic field cannot set a stationary charge into motion. Magnetic field cannot do that. Only electric field. When you put an electron inside an electric field, electron will start motion. Right. If you put an electron inside a magnetic field, it will stay at that point where you put infinitely. That's why you will say that magnetic field cannot start the motion of a charge. Cannot start the motion of a charge. If you want to move a charge, what you have to do? You should use first electric field. Only by this way you can start the motion of a charge. An electron can be moved only by electric field, not by a magnetic field. So, magnetic field cannot set a stationary charge into motion if unable to start the motion, which means there is no magnetic force acting on it. Because force causes the motion. So when you put a charge inside a magnetic field at rest, what does at rest mean? Its velocity must be zero. So magnetic force acting on the charge is going to be zero. So no magnetic force acts on the stationary charge in a magnetic field. Yeah, if velocity is zero, magnetic force is zero. If velocity is zero, no force acts on it. And magnetic field cannot set a charged particle into motion. But what do you have to do? Maybe lose electric field. Electric field will start the motion of the charge. Then, first thing we have to know was this, and we got it. If you put a charge inside a magnetic field at rest, this magnetic field cannot start the motion of the charge. Only electric field. This is a mystery exam question. Now open the mystery exam question part. Turn over the page. Let's see the page. Okay, where is the question? Let's find it. Question number 17. Question number 17. Did you find 17? It cannot set a resting electron into motion. Now, which is this? A. Electric field. No, electric field always sets the particles into electric field. Stationary magnetic field.
Stationary is 0.
Stationary, not changeable. Yani magnetic field. Don't think about stationary. Magnetic field. Magnetic field cannot set a charge into motion. So answer is going to be stationary magnetic field. Okay, what should we do in this case? You have to use electric field. You should set particle into motion. Then it must enter inside the magnetic field. Yani, charge must be moving inside the magnetic field. This is how a charge experiences a magnetic force. First, you should set charge into motion by using electric field. It must start moving. Then you should let this charge enter inside magnetic field. Yani charge must be in motion because of some other field. So this is how magnetic force acts on a charge. And magnetic force may, I said may, not always. And magnetic force may act on a charge in a magnetic field if charge is initially in motion. How can we make it initially in motion? By using electric field. You can set it into motion and send it into the magnetic field. Then there may be a magnetic force acting on the charge. So the magnitude of the magnetic force, I am going to represent it by F magnetic. Acting on a moving charge, absolutely, charge must be moving, otherwise there will be no force. Acting on a moving charge with a speed v. Charge, what is the symbol of charge? Q. This charge must be moving in a magnetic field, B. Magnitude of the magnetic field is going to be multiplication of these three. Multiply them all. Q, V, B, V, Q, B, B, Q, B. Which one do you like saying it, okay? But there is a sine theta. Q, V, B, sine theta. What is this theta? Theta is the angle between magnetic field vector and velocity vector.
This is your exam question.
Can be. Yes. What is theta? Theta is the angle between magnetic field vector V and velocity vector V. So QVB sine theta is the equation for calculating magnitude of the magnetic field. So then this theta is the angle between B and V, and according to this angle, magnitude of the magnetic force changes. Now coming. If this angle is 90 degrees, what does it mean? Charge is moving perpendicular to the magnetic field lines. Angle between V and B, 90 degrees. And sine 90 is what? 1. What does it mean? Maximum magnetic force acts on the charged particle. If particle is moving perpendicular to the magnetic field lines. Magnetic field lines are horizontal, particle is moving in vertical. So angle between them is 90. If angle is 90, sine 90 is 1, force becomes the maximum, greatest force. So greatest force or maximum force acts on the charged particle. At what angle? At what angle? 90 degrees. This is mystery 10 question. So at angle of 90 degrees, the maximum magnetic force acts on the charged particle which is moving in the magnetic field. What if charged particle is moving parallel? So parallel means in the same direction or in the opposite direction, are they? Yes. If the particle's velocity and b are in the same direction, angle between them is 0. No, same directed vectors, angle between them is 0. Sine 0 is what? Sine 0 is 0. In this case, magnetic force becomes, yeah, if a particle moves in the same direction of the magnetic field, magnetic force is 0. What about opposite direction? So, velocity is to the left, b is to the right, angle between them is how much? Oppositely directed vector, angle between them is 180. Don't forget this. If two vectors are in the same direction, angle between them is 0. If two vectors are opposite direction, angle between them is 180. Okay, 180 sine also 0. Sine 180 is also 0. That's why magnetic force is 0. Then, if I ask you a question, at which of the following angle magnetic force acting on the charge moving in magnetic field is 0? A, 0. B, 180. C, 90. D, both A and B. Both A and B. 0 degrees and 180 degrees. Magnetic force acting on the charge is 0. Okay. What if angle is not 90 and 0 and 180? What if angle is 30? What is angle is 30? So we should calculate, huh? What is sine 30? 0.5. You know, 1 over? Right, instead of sine 30, 1 over 2. Right here, 1 over 2. So it's going to be QVB multiplied by 1 over 2, correct? What does it mean? Yeah, you are going to divide QVB by 2. Now, what is QVB? Maximum magnetic force. Maximum magnetic force. So if angle is 30 degrees, the force acting on the particle is half of maximum. Half of maximum force. This is also a mystery question. If magnetic force acting on a charge is less than maximum, in here greater than 0, but for 30 degrees, it is 1/2 of the maximum magnetic force. Now turn over open again mystery exam questions. Open that page. Let's find the question. It is this one, 12. Okay, let's answer 12, then the next one. At which angle between the direction of the uniform magnetic field and positive charge particle movement, magnetic force on the charged particle is equal to half of its maximum value? At what angle? 30 degrees. 30 degrees. When angle is 30 degrees, so magnetic force acting on the charge is half of maximum. Okay, at what angle it's maximum? 90. At what angle it is 0? 0 and 180. So these are the possible mystery exam questions I think in this title.
Can you say parallel?
Parallel is possible. Parallel is 0. Perpendicular? 90 but maximum. 30 is half. Okay. And one more key information to you. There will be a magnetic force acting on the charge if charge crosses the magnetic field lines. Yani charge, while it's moving, it must cross magnetic field lines. At 30 degrees, is it crossing the magnetic field lines? Yes. At 90? Yes. But at 0? No. At 180? No. So, charge must cross magnetic field lines. In this case, you can say that there's a magnetic force acting on the charge. Now we are going to solve one problem. A proton moving east. So, motion of the proton is to the due east. Experience a force of 8.8 times 10 to the power negative 19 Newton upwards due to the Earth's magnetic field. Yeah, a proton is moving inside Earth's magnetic field. At this location, the field, the magnetic field of the Earth has a magnitude of 5.5 times 10 to the power negative 5 Tesla. So, and direction is to the north. And we know that magnetic field of the Earth is from south to the north. We learned this before. Find the speed of the particle. Okay, in this question, only magnitude of the speed is asked, but in the coming problems, we are going to solve it by direction as well. And remember, we studied 3 sets of directions. This is which set? The third set. North, south, east, west, upward to the sky, downward to the ground. Now, this is the third set. So, because direction is given as east. Okay, let's draw the directions of the third set. So just I'm going to show it to you because we are not going to find the direction of velocity, but just I want to show you how to use it. Okay, this is the north pole, north of the north direction, so it's up to the board. South is bottom to the board, so this is going to be the east, this is going to be west. Now according to this, the given proton is moving east, so you are going to draw velocity vector to the east. So velocity vector is going to be east, V is going to be to the east. And this proton is inside a magnetic field, Earth's magnetic field. At that location, Earth's magnetic field is to the north. So it's going to be like this. So B is to the north. Tell me now, what is the angle between these two vectors? 90 degrees. What does it mean? Maximum magnetic force acts on this charge. So when the angle between V and B 90 degrees, so maximum magnetic force acts on this proton. So then let's use the equation. What is the equation for maximum magnetic force? F maximum is equal to Q times V times B. Okay, Q in the problem it will be given. I forget to write, but it's going to be given. Q for electron and proton, both of them, 1.6 times 10 to the power of negative 19 coulomb. So F maximum is given. Q is given. And V is given. What is unknown? V is unknown. So can we find easily? Yes, one unknown. We can find this. So simplify Q and B. Divide by QB. And divide by QB. Simplify Q and B. V is going to be F maximum divided by QB. And what is maximum magnetic force acting on the charge? 8.8 times 10 to the power of negative 19 Newton. So this is the maximum force. Let's insert into the equation. 8.8 times 10 to the power of negative 19 Newton divided by charge of proton. How much? It's given 1.6 times 1.6 times 10 to the power of negative 19 multiplied by magnetic field at that location is given as 5.5 times 10 to the power negative 5 Tesla. B is also given. So 5.5 times 10 to the power of negative 5 Tesla. Don't forget to use the bracket for denominator. Only at begin and at the end you should put denominator brackets. Result is going to be 10 to the power of 5 meter per second. So 10 to the power of 5 meter per second is the speed of this proton inside this magnetic field.